Exercise 930, or 9.30, wants you to predict the products that are expected when each of the following alkenes is treated with a peroxy acid, such as MCPBA, followed by aqueous acid. And so that's that recipe that we've seen before. You're either going to have a peroxy acid written in, sort of with 3 oxygens and a hydrogen, like that, or you'll have MCPBA. That turns the alkene into an epoxide, like we discussed in the previous video, and then you have hydronium, which bursts the hydroxide open. First it protonates the oxygen and the epoxide to make it a better leaving group, and then the water comes in and attacks it as a nucleophile to give you, from the opposite direction, to give you your anti-dihydroxylation. So we went over the mechanism for that in that separate video. In this one, let's think about those mechanistic details just in terms of synthesis. So if you have this alkene and you treat it with, first, either any peroxy acid or specifically metachloroperoxybenzoic acid, MCPBA, and then follow that up with an acid wash with H3O+, you'd say, okay, I see an alkene, I know we're doing an addition reaction, as opposed to substitution or elimination. So I'm going to redraw that carbon skeleton exactly as it is, just without the pi bond. Excuse me, we're going to use those pi electrons to stick something new onto this molecule. We're going to use that extra molecular glue we have there, which is what electrons are, to stick something new on the molecule. Now here, you would look at the recipe, you would see that you have a peroxy acid followed by an acid wash, and so you'd say, okay, anti-dihydroxylation. The 2 carbons that were in the double bond, that's where I'm going to put 2 OHs, 2 hydroxyl groups, and they're going to be facing an opposite direction. So if one is coming out at me, the other one will have to be going away. Now, we need to make sure that that is properly drawn, and so if the 4 bonds are drawn explicitly, you need to have 2 in the plane, 1 coming out and 1 going away, so that methyl group there will have to go away. And then, with the other one, 2 bonds in the plane, 1 going away, the other one should be coming out at us. So that methyl group would be coming out at us. So that's one of your products. The other product is going to be the enantiomer of that. There's no reason why, because this molecule is flat, the alkene is flat, each of the carbons in it is trigonal planar. There's no reason for one side of the molecule to be more reactive than another. You get a 50-50 mixture of the reaction happening on each side. So we have to draw the enantiomer, so we switch all of these bonds. If it's coming out, we make it go away. If it's going away, we make it come out. And so likewise, if we have one that's coming out at us, we'll make it going away. And if we have one that's going away, we'll make that bond come out. And by doing that, we switch the chirality of each of those chiral centers. If you switch all of the chiral centers, you get the enantiomer. So these are your 2 enantiomers. You'd get them in a 50-50 racemic mixture when you do this anti-dihydroxylation with a peroxy acid and that alkene. Okay, so B is asking for a similar thing. It says, what if you treated this with either any peroxy acid or MCPBA specifically, metachloroperoxybenzoic acid, as a first step, and then as a second step you did an acid wash. So the first step creates the epoxide, the second step breaks it open. Well, you would see the original molecule, the alkene. You would say, okay, a pi bond, that means I can do addition as opposed to substitution or elimination. You'd look at the recipe to see what you're adding. You'd see a peroxy acid followed by an acid wash, and you'd say, okay, I'm adding 2 hydroxyl groups, and they're going to be anti to each other. So if one hydroxyl group is coming out, the other will be going away. And since those are chiral centers, you will want to draw both enantiomers. So the other enantiomer, to get the other enantiomer, you switch the configuration. Any bond that's going away, you make that come out. Any bond that is coming out, you make that go away. So you get a 50-50 mixture of those two enantiomers. When you do anti-dihydroxylation with this pi bond. Okay, for C, same thing. What if you're treating that with either any peroxy acid or MCPBA specifically, metachloroperoxybenzoic acid? Those turn the alkene into an epoxide, and the epoxide is then burst open with an acid wash. So you'd see the alkene, you'd say, okay, what I can do with this is an addition reaction. I have this pi bond, that's extramolecular glue I can use to add things onto this molecule. So we're doing addition as opposed to substitution or elimination. Then you'd look at the recipe, you would see that you have a peroxy acid followed by an acid wash. That's the recipe for anti-dihydroxylation. So you'd redraw the carbon skeleton exactly as it was, but without the pi bond. And then on each of the atoms that were in the double bond, you'll add an OH. Now, if one of the OHs is coming out at you, the other OH has to be going away, because this is anti-addition. So that is one possibility, but those are two chiral centers that we've created, so we get both of the enantiomers. So we switch each of the branches, the bonds, and if it was coming out at us, we make it go away. If it was going away from us, we make it come out, and so we get a racemic mixture, a 50-50 mixture of those two enantiomers when we do anti-dihydroxylation with this alkene. For D, the question is the same. What if you treat that with either any peroxy acid, RCO3H, or specifically with metachloroperoxybenzoic acid, MCPBA, followed by an acid wash, so hydronium? Well, the peroxy acid, so we see the alkene, we know we're doing an addition reaction as opposed to substitution or elimination. Then you look at the recipe to tell what you're adding. You see a peroxy acid that turns an alkene into an epoxide, followed by an acid wash that bursts the epoxide open to give you the anti-dihydroxylation. We're going to be adding two OHs anti to each other. So these are going to be adding to the two carbons that were in the double bond. If one of the OHs is going away from us, then the other OH would have to be coming out at us. Now in this particular example, we don't have any chiral centers. This carbon here on the end has two hydrogens on it, so it's not bonded to four different things. And if you look at the carbon in the ring, so if you look at this carbon in the ring, that carbon, if you go around the ring in one direction and go around in the other direction, you run into the same stuff at the same point, the same distance, which means that going around that ring one way or the other is the same, and so that carbon is not bonded to four different things. Because of that, because we don't have any chiral centers, we would not draw the enantiomer. The enantiomer would just be drawing this all over again. So you draw this molecule, and technically you wouldn't even have to include the stereochemistry, but I'm going to do it just to emphasize the fact that this is anti-addition. Okay, for E. So they're asking, what would happen if you took that alkene and you treated it with any peroxy acid, so RCO3H, or specifically MCPBA, metachloroperoxybenzoic acid, followed by an acid wash, so hydronium. Well, the peroxy acid turns the alkene into an epoxide, and the hydronium bursts the epoxide open and adds another OH. So this, you'd recognize from this recipe that you're doing anti-dihydroxylation. So you'd redraw the carbon skeleton as it was, but without the pi bond. To each of those carbons in the pi bond, we're going to add a hydroxyl group, an OH. Now, if one of the OHs is coming out at us, then the other OH will be going away. Now, those are both chiral centers, and so we're going to end up getting a racemic mixture of that and its enantiomer. The original molecule was flat, and so both sides of the molecule could have done the reaction equally well. And so if you get to both sides, you get, if each side reacts and gives you a different enantiomer, so you'll get a 50-50 mixture of each enantiomer, a racemic mixture. So any bond that was coming out at us to get the enantiomer will make that go away and go away from us, and any bond that was going away from us will make that coming out at us, solid wedge. That flips every chiral center, and when all the chiral centers in a molecule flip, you get the enantiomer. So if you did anti-dihydroxylation with this alkene, trans 2-butene, that would give you these two, a 50-50 racemic mixture of those two molecules. All right, last one, F. They're asking what would happen if you treated this first with any peroxy acid, RCO3H, or specifically with MCPBA, metachloroperoxybenzoic acid. Those are both peroxy acids, it's just MCPBA is a really common one. So that followed by hydronium, what would you get? Well, you'd see the alkene, you'd see the pi bond, and you'd say, okay, what I can do is addition here, as opposed to substitution or elimination. And you'd look at the recipe to tell what type of addition you're doing. You'd see the peroxy acid, that turns an alkene into an epoxide, then followed by hydronium, that turns the epoxide oxygen into a good leaving group, and then the water comes in as a nucleophile and attacks on the opposite side of the oxygen that's already there, as we saw in the mechanism, the video that we made. We talked about the concepts behind this reaction. So you'd see this recipe as anti-dihydroxylation. So you'd redraw the carbon skeleton how it is, but without the pi bond. And the two atoms that were involved in the pi bond, those are the two atoms where you're going to be adding an OH, a hydroxyl group. Now, if the OH is coming out at you on one of them, it will have to be going away from you on the other, because this mechanism gives you anti-addition. The last thing you want to make sure you do is make sure it's tetrahedral, drawn that way, so you have two bonds in the plane, one coming out and one going away. Finally, we have two chiral centers here, and so there's no reason why one side of this original molecule would be more reactive than another. The pi bond is flat. The two carbons involved in it are both trigonal planar, and so the reaction could have happened on either face of the molecule. So you end up getting a racemic mixture of the two enantiomers that you get when the opposite faces each react. Now to draw the enantiomer, you switch each of the bonds. So if a bond was a solid wedge, you turn it into a dashed wedge. If a bond was a dashed wedge, you turn it into a solid wedge. And likewise, with the bottom one, if the bond was a dashed wedge, you turn it into a solid wedge. And so these are the two enantiomers you would get in a 50-50 ratio, a racemic mixture, if you took any peroxy acid followed by an acid wash and you treated it with this alkene. So hopefully this and the previous video explaining how this reaction works will give you some help in predicting the products of anti-dihydroxylation.